Hello everyone. In this recording we will be talking about linear regression model. If you go back to chapter 1, we talked about studying of business analytics is divided into three categories: descriptive statistical analysis or descriptive analytics, predictive analytics, and prescriptive analytics. And we assume that you know what does it mean by descriptive statistics or analytics, which is that one that you have done in basic or introductory statistical classes. And in this class, we focus on predictive analysis. And specifically in this chapter, we are going to introduce regression analysis, which is the most widely used technique in predictive analytics. The question is, why do we need regression analysis? We need regression analysis for two reasons. Number one, to assess the relationship between variables. We need to know the relationship between variables, because sometimes we believe that there is a relationship between variables. The second reason is to predict the outcome of a target variable on the basis of several input or independent or predictors variables. So the idea is to predict a specific variable based on other bunch of variables. For example, if a firm increases advertising expenditures by, let's say, $100,000, then we may want to know the likely impact on sales. So you put some money on advertising. So what is the impact is going to be on the sales? In this case, we use regression analysis. Or maybe you would like to predict the price of a house. If predicting a price of a house, it's going technically depends on maybe the size, location, the quality, the city, location we said. So regression analysis is going to be used in both scenarios. So in the coming recordings, we will be discovering first the OLS method, which is ordinary least squares method for estimating linear regression model, where the relationship between the target and input variables is assumed to be linear. Also, we use the estimated model to make predictions about target variable, and we will develop interval estimates for prediction. Not just we will predict, we will develop interval estimates for the predictions. Also, we will then examine the number of goodness of fit measures and conduct hypothesis testing in order to assess which input variables or which predictors variables matter the most, which variables have the most impact on the target variable. Finally, we are going to examine the importance of the assumptions on the statistical properties of the OLS estimator, also the validity of the testing procedures. Finally, we are going to address common violations to the model assumptions and what are the consequences when these assumptions are violated. We will offer some remedial measures. So this is going to be the summary of this chapter. It's going to be long, kind of. So that's why we're going to have different recordings. And after every section, we are going to do another recording as an example on R. So regression analysis is one of the most widely used techniques in predictive analytics. We use it to capture the relationship between two or more variables and to predict the outcome of a target variable based on several predictor variables or input variables. Regression analysis allows us to make assessments and robust predictions by determining which of the relationships matter the most and which one we can ignore. We formulate a mathematical model that relates the outcome of a target variable, called the response variable. So the target variable is going to be the outcome, which is another name, response variable, to one or more other input variables called predictor variables. So we call them either input variables or predictor variables, or sometimes we call them independent variables. And again, for the target variable, we call it target or response variable. Sometimes we call it dependent. Consequently, we use information on the predictor variables to describe or predict changes in the response variable. Regression models are known to perform well for making predictions, but we have to be careful here. Sometimes, however, they fail to establish a cause and effect relationship between the variables because of the largely non-experimental nature of most applications. Most applications are not experimental. And the regression model, the one that we're going to build, may appear to search for causality, but it detects correlation. Again, correlation, not causality. Causality can only be established through randomized experiments or advanced statistical techniques, and this is above or outside the scope of our class. No matter the response variable that we choose to examine, we cannot expect to predict its exact value, its unique value. If the value of the response variable is uniquely determined by the values of the predictor variables, we say that the relationship between the variables is deterministic. And an example of this, in physical sciences or in mathematical sciences, if you multiply the mass by the velocity, you get the momentum. So this is deterministic relationship. So if you multiply m, the mass, by the velocity v, you get the p, like the momentum. But in fields of most of other fields, like in social sciences or in business or marketing, we tend to find the relationship between the response variable and the predictor variable is stochastic. It's not deterministic, it's stochastic. Why? Because due to the omission of relevant factors. These factors, they are most of the time are not measurable. Okay? So the omission of relevant factors that influence the response variable. For example, if you try to predict an individual's salary, the individual's natural ability is often omitted because it's extremely hard or difficult to quantify. You cannot quantify the natural ability, right? So that's why we say it's a stochastic, it's not deterministic. So what is the objective? The objective is to develop a mathematical model that captures, so this is what we're going to do, by the way. We're going to develop a mathematical model that captures the relationship between the response variable y and number of predictor variables, k, maybe 2, 3, 4, 5, we don't know. Is to capture the relationship between a response variable, the outcome variable, which is y, and the k predictor variables, x1, x2, x3, up to xk. The model must also account for some randomness. There is a randomness that is a part of real life. So in order to develop a linear regression model, we start with a deterministic component that approximates the relationship we want to model. After that, what we do, we add a random error term to it, making it stochastic relationship. So what are the components of the linear regression model, as we said? The components, we're going to talk about the components, but the components are the response variable, the predictor variables, and the error term. So we are going to use economy theory, intuition, and statistical measures to determine which variable or which predictor variable might best explain the response variable. Okay. A regression model treats all predictor variables as numerical, and this is important, and you have to keep it in your mind. The regression model treats all predictor variables as numerical, but some observations are categorical. They have some categorical variables, So what we have to do, as we did in chapter 2, they must be converted into numerical values. Just to recap, to get back, what does it mean by having a numerical variable? The observations of a numerical variable represent meaningful numbers. The observations of a categorical variable represent different categories. For example, the income is a numerical variable, and the marital status is a categorical variable. And if you recall chapter 2, that a dummy variable is also referred to an indicator or binary variable takes numerical values, zeros, ones, that describes two categories of a categorical variable. If you have a categorical variable, sometimes you have to establish a dummy variable because the dummy variable takes numerical values. And if you remember, we talked about this. For a predictor variable that is a dummy variable, it's common to refer to the category that assumes a value 0 as the reference category or the benchmark category. And all comparisons are made in relation to the reference category. For instance, in the case of the dummy variable, categorizing a person's sex, we can define 1 for male and 0 for female, or the opposite way around. In this case, the reference category would be females. If you do the other way around, if you define 1 for female and 0 for male, where the male would be the reference category. So the main idea of this slide is the regression model treats all predictor variables as numerical. So we have to make sure to do some data transformation for the categorical variables before we proceed. If a linear regression model uses only one predictor variable, as this example here, then this slide is about to be a technical a little bit. We will be seeing this in a real example later. So if the linear regression model uses only one predictor variable, then the model, we call it simple linear regression model. And we write this as you see, y equals beta naught plus beta 1 x1 plus the error. Beta naught and beta 1, both of them are unknown parameters. Unknown parameters again. These are unknown. We don't know. So this is the model that we are trying to build, right? And betas are Greek letters. And x1, what is x1? x1 is the predictor variable, and y is the response variable. For example, if we talk about, let's say, the example that we mentioned earlier about the sales and advertising. So advertising is going to be my x1, and we are trying to predict the sales after putting some money on advertising. Okay, so this is the deterministic component of the linear regression. After that, you're adding the error. You're adding the error e. After adding the error, you are going to have stochastic relationship. And this is linear. I mean, if you look at the equation, it's just a linear equation. So this is a straight line. This is a straight line. This is very simple mathematical equation, straight line, and we have two values here. The value with the x represent the slope of a line. It's a linear, so it's a line. So beta 1 is straight. Beta 1 represent the slope, which is the rate of change, the slope, and beta naught represent what? The intercept, y-intercept, right? So we have two parameters. The beta 1 determines whether the linear relationship between x and y is positive, so if this is positive, or negative, if this is negative. If this is negative, so we have a positive relationship between x and y. If this is negative, so we're going to have a negative relationship between x and y. Because the idea is, what is the difference between this equation and the expected value of y? So this one, the first one, the difference between this and this one, the y equals beta naught plus beta 1 x1 plus the error is a standard form of the simple linear regression, and the error represents the random error term, the one that we add to make the relationship stochastic, because it's not deterministic, because we have a difference between the actual values of y and the observed values of y, and the values predicted by the relationship is this one, beta naught plus beta 1 x1. The other one, the other equation, is the expected value of y equals beta naught plus beta 1 x1. This equation represents the conditional mean of y. So this is the mean of y given x1. So this expression for the expected value of y based on the linear relationship between y and b naught plus b1 x1. So the error term here is not explicitly mentioned, but it's implicitly considered in the process of estimating the coefficients beta naught and beta 1. So I don't want to focus on the technical stuff here, but it's enough to know the expected value of y is going to be beta naught plus beta 1, and we are going to see this in the next slide. So the components, as we said, we still here. If beta 1 is a positive, so we're going to have a positive relationship. So this is the expected value of y for different values of beta 1s and beta naught. If beta 1 is 0, then we have no linear relationship. If beta 1 is negative, so we can have a negative linear relationship. If beta 1 is positive, we're going to have a positive relationship. We can easily extend that simple model to include more than one predictor variable. We can have more variables. And the resulting model is going to be this. And we call it multiple linear regression, which is y equals beta naught plus beta 1 x1. Let me use, where is it? Pointer, laser, okay. Beta naught, beta 1 x1 plus beta 2 x2, etc. We cannot visualize this. If you have a linear, we can visualize up to 2 variables. You have 3D, but beyond this you can't. But at least you know what does it mean by the slope, right? And you know that this is the intercept, right? What happens if you have a dummy variable? You just replace x with d for a given predictor variable if it's a dummy variable. So we will be saying, by the way, just for simplicity, we will refer to the simple linear regression or multiple linear regression as a linear regression model. So linear regression model, it's going to, as a term, is going to be used for both or any linear regression model, either simple or multiple. And the other thing that we would like to know is beta naught, beta 1, beta 2, all of these are population parameters. And these are unknown. And we don't know them. We don't know this relationship. This is the most important idea in this slide. Betas, we do not know them. These will be estimated. What are the estimates of betas? B naught, B1, B2, up to Bk. And how we are going to estimate this? We're going to use sample, because these are the population. This is the population equation. But we cannot access all of the population. We have access to sample data. That's why we will not be able to have betas. We will have access to beta. We will estimate the betas. And we will be able to obtain B naught, B1, B2, etc. Okay, so what's going to happen? B naught, B1, B2, up to Bk, they are going to represent the estimates of beta naught, beta 1, beta 2, etc. Then we are going to form what we call sample regression model. Sample regression model. It's going to be, and this is going to be the equation, y hat, which is the predicted value of the response variable. Remember, this is the predicted value of the response variable given specific values of the predictor variables x1, x2, x3, etc. So y hat is going to be b naught plus b1 x1 plus b2 x2, etc. So it's a predicted value. It's a predicted, right? We have observed. The observed value of y is going to be y. And the difference between the observed and the predicted is y minus y hat. And this is an important term. We call it residual, which is the error. The error. So the error, this error, the goal is try to minimize the error as much as we can. Excuse me. And we are going to use a method called OLS, ordinary least squares, to try to minimize the error sum of the squares, SSE, which is we add all of the errors. We square the errors first, then we add all of them to get the error sum of the squares. And the goal is to minimize this as much as we can. Why to minimize it? Because the goal is to have y hat, the predicted value, equal as much as possible, equal to the observed value. Someone is going to ask me, if you have the observed value, why do we do prediction for that value? If you have the values already, why do we need to do prediction? Yeah, but this is not the problem. The problem is not with these values that we do have in our hand. The goal is to build the model to predict new values. Okay? So that's why we need to do that, like kind of a testing that this model works well or do. Excuse me. Yeah, so this is the thing that we are going to do, which is the estimating the linear regression model. And this is an example. In this graph, we can see only one predictor variable. And the scatter plot, these are points. This is my x values. This is like, let's say, the predictor variable. And this is the y, which is the response variable. Okay? And we have values. Maybe we can think about the x as the size of the house. No, it doesn't make sense here. It's decreasing. So we have already observed values, the dots, and we built a model. This model we built, we get this equation that the predicted value is equal to beta b naught plus b1x, and it's presented by this straight line. So if I, for example, would like to check if x is this value here, what is the predicted value of y? You just go up, go up, go up. You look here, this is the predicted value of y. So this is the predicted value of y. But the question is, what is the observed value of y? What is the observed value of y? Is this one. So what have you predicted here is not the same as the observed. So we have an error. So the distance between the observed and the predicted, we have a distance. So we have differences basically between the observed values and the predicted values. For instance, look at these. They're matched. So the observed and the predicted values. But we have an error here. Right? So the goal is to try to minimize all of the squared error, to make the distances as small as we can without getting into a trouble of something we call overfitting or something. We'll be talking about this later. But this is the goal. The goal is creating a good model that can predict what's going to happen. And again, I will repeat the question. Maybe some people are going to say, if you have already these values, why you are building a model? Yes, we are building a model to study the relationship between both of the variables and try to make some forecasting or predicting to the future what's going to happen. If I give you this value, what's going to happen? If I give you this value somewhere here, what's going to happen? If x is here, what's the value of y? If x between any, if x is any value on the straight line here, or on the x-axis, what's the value of y? The predicted value of y. So that's why we are building a model. Okay. It's important to be able to interpret the estimated regression coefficients, and mathematically the intercept estimate B naught represent the predicted value of y hat when each predictor variable assumes a value of 0. Again, if each predictor variable assumes a value of 0, then what we're going to get, you're going to get the beta naught. Makes sense. In many applications, it's not possible to provide meaningful interpretation for the intercept, and we're going to see this. What about the slope, like the B1? For each predictor variable, the corresponding slope coefficient, and this is important, B1 is the estimate of beta 1. B1 is the estimate of beta 1. And what does this measure? What BJ, B1, B2, B3, B, etc. BJ, we say BJ because we have many predictors. What does this value represent? What does this value measure? BJ, whether B1 or B2 or B3 or B4, etc. It measures the change in the predicted value of the response variable y hat given a unit increase in the associated predicted variable xj, holding all other predictor variables constants. In other words, it represents the partial influence of xj on y hat. In the linear model, you are only studying the impact of this independent variable on the response variable holding other predictor variables constant. In other words, we study only the partial influence without having any interacting influences from other variables. So this is the meaning or the way that we are going to interpret the betas, beta naught, beta 1, or sorry, B1, B naught, B1, B2, B3, etc. Okay. We also are going to do something which is building interval estimates, because it's not enough just to do a prediction. We will have to build estimates. The prediction is useful, but we need to be aware that it's subject to sampling variations. In other words, the prediction will change if we use different sample to estimate the regression model. That's why, as I said, we are going to create estimates and interval estimates. So we will make a distinction between the interval estimate for the mean, and we will, again, you will see all of what we have said today in an example, okay? We will have a distinction between two things: the interval estimate for the mean, which is the expected value of the response variable y, and the interval estimate for the individual value of y. We will have two things: interval estimates of the mean and interval estimate for the individual y value of y. The first one we call it the confidence interval, which is the interval estimate for the mean, and the second one we call it the prediction interval. For given values of the predictor variables, we can think of the confidence interval as the range that contains the mean of y, and the prediction interval as the range that contains the individual value of y. And again, we will be using the same point estimate for constructing both interval estimates. Finally, due to added uncertainty in the predicting the interval value of y, the prediction interval is always going to be wider than the corresponding confidence interval. So the prediction interval is always wider than the confidence interval, and we will be seeing this in an example. We talked about this already. The last thing we're gonna say maybe is about the categorical variable. So far we have used a dummy variable to describe categorical variable with only two categories. Sometimes the categorical variable may be defined by more than two categories. In some cases, in these cases, we use multiple dummy variables to capture all categories. We did this in chapter 2, by the way. So the mode of transportation used to commute to work may be described by three categories: public transportation, driving alone, and carpooling. We did this example. We define two dummy variables because we have three categories, D1 and D2. D1 equals 1 for public transportation, 0 otherwise. D2 is going to be equal 1 for driving alone, 0 otherwise. For the three category case, we need to define only two dummy variables, as I said. So carpooling is going to be the reference category. When D1 equals D2 equals 0, we're going to have carpooling. Given the intercept term, we exclude one of the dummy variables from the regression, where the excluded variable represents the reference category against which the others are assessed. And we're going to see this. If you include as many dummy variables as there are category, then their sum will equal 1. If you add a third dummy variable, D3, that equals 1, to represent carpooling, then all of the observations, D1 plus D2 plus D3 equals 1. This creates a problem. We call it perfect multicollinearity. This will be discussed later in this chapter. And this situation, we call it dummy variable trap. Dummy variable trap. This is everything for the first part of the chapter. After that, I'm going to go over an example. Thank you.